last session. And if there are some slides in this lecture, we will actually continue with them with the next lecture. So here is a plotting for the behavior of the algorithms in general. So in the green area, we have the constant one, big O1. Okay, that is when we have like a constant operation, number of operations, we have formula, and we just replace n with some numbers and calculate. It's just one n operation. But then we have the big O log n. This is the logarithmic. And if we go to the upper bound, the red one is actually, we have the factorial, we have the exponential, and we have the quadratic behavior of the algorithms. And we try in our when we build the algorithm is not to go to the red area. It's very much better if we are keep on the green, but this is not always the case. Sometimes you have an algorithm that you can't control the behavior. Like it can be solved with log n. But we try out to solve the problem using that behavior. If not, we try to go above, but we try to avoid this as much as possible, the red area. As we see, the growth rate of them is very high. Here is an example with numbers. Okay, here when n is actually 10, if the behavior can be represented by log to the base of 2, actually log n of n, then the number of operations, if we calculate that, it's actually 2. This means like if I have an array of 10 elements, then I want to find out for example, a specific number there, and if the behavior of my algorithm is actually behaving log times log of n, then it means like I will execute 2 operations only. Okay? But if the algorithm is using a for loop of the size of the problem, which is 10, then I will do the operation 10 times. And if it's factorial, it is actually 10 to the power of 5. And this is, by the way, it's not exact number. It's relative numbers here. So we try, if you try to calculate, for example, here log n, it's 3 when n is actually 10, but it's not exactly 3. It's approximation. Okay, so it's 3 point something. Therefore, when it's n log n, you expect to have 10 times 3, which is 30, but we have 33 here because I said it's the log of 10 is actually not 3, it's 3 point something. So this is an approximate numbers. But look to the problem when n is actually like really huge, for example 10 to the power of 6, then if we are talking about a factorial behavior of my algorithm, then this means like I will execute 10 to the power of almost 3 million operations, which is like very, very huge number. So this is in terms of operation and growth rate. Now I try to picture the complexity for you just to understand it. If you want to sum the percentage numbers of, and we have a for loop, then what we do is like, we go from, this is I here, so we need 10 times summation, okay? So each time you go to the for loop, you sum a number to the sum, you add a number to the sum, and so on and so forth. This is another picture when we actually have 2 nested for loops, okay? And you can think about the column as the I, and the rows is actually the j. And you can see like when I is 1 and j is 1, we do just one operation. But when I is 2 and j is actually, sorry, you have to go with 1 when I is equal to 1, and then j is equal from 1 to n. So this, you need to repeat it several times. And this is what we, why it's listed here. It's like the maximum behavior is will be like n times n. This is when j is actually goes to n and I is actually n, so we have a square. This is the maximum thing, but you could actually have this behavior because here j is not going to n, it's actually going to I. So it is depending on the number of I. When I is 1, j is actually 1. When I is 2, j is actually this is not, here it's not the maximum, it's less than the maximum, but the maximum is this one. Okay, this is the worst case. Okay, that both of them is actually going to end. What we try to explain using the theory in the previous slides when we calculated C times Gn is the following. So if I have a for loop, like two-nested for loop here, you can say the first for loop is actually goes to n. Okay? And we have a nested for loop, it's again n, so n times n, and then we can describe the behavior of it and say this is actually big O to n to the power of 2. We have some rules, we will explain that. But imagine that you have the following, you have the same algorithm, but after it, you have two nested for loop, and we agreed that this is n to the power of 2. But then we have another for loop, it's not nested, okay, it is just a for loop, and it goes to n, then this is a plus n, okay, it's not nested, it's a third for loop, not nested, okay, so this is two nested for loop, n to the power of 2, then we have another for loop, it's n, and then we have 1000 constant operation, okay, it's like printing, I don't know, just statements in your program. Imagine not 1000, just 2 statements for printing. This is our constant. We are not doing such operation, just perform the operation here. It's like plus 2, so because we have 2 constant operations. Okay, if we want to decide about the complexity of this algorithm, we will say that the complexity is big O of n to the power of 2. Okay? And what will come to your mind is that how? How is this one is an upper bound for this one? This is what we have explained in the theory, okay, in the previous slide. This is absolutely is greater than n to the power of 2. Okay? But when we say that big O of n to the power of 2, this is not the case. This is not bigger. So this will be actually less than this one. Why? Because when we have this symbol, it means that there is a constant, C, times n to the power of 2 at some point when we have n not equal to something. Okay, I don't know. Here in this case, you have to calculate it. Then this big O of n of n to the power of 2 will start be an upper bound for this algorithm, and this is what we have explained. Okay, this is the theory, but from this slide and the next slide we will just use the big O, and we'll never talk about C, and we'll never talk to n about n. Okay, so that's just for you to understand the logic. So if we have constant statement in my algorithm, then the complexity is constant. When we have a printing statement, when we have just only a definition for a variable, like say integer x equal 5. Okay? When you have a formula, these are all constant. You are not doing loops, okay? You don't have branches, if a statement. These are constant, and we say, okay, the size of the problem is 1, and even if it's double, that we have 2 constant, 3 constant, 10 constant operations, it's always the behavior of my algorithm is constant, and we say it's 1. Okay? When we have the behavior is actually log n, logarithmic, and we double the size of the problem, then the result it will be 1 plus log n. How we calculate this? It's just actually the behavior of your algorithm is logarithmic, right? It's log n. But we double the size of the problem, so it's log 2 times n, and this actually can be simplified as log 2 plus log n. Log 2 is actually 1 because this is log 2 to the base of 2. Then it's actually 1 plus log n. Okay, so this is when we double the size of the problem, and then we have n log n is the same. You can try it out. So we have when we double size the problem, it's 2n log 2 times n. And it will be n to 2n log n plus 2n. As a simplification, this is, if you want to understand from where this number comes from, you can look to this one. And so on and so forth. This is, if you double the size of the problem, you can look to the table. You don't need to remember it, but just only for your information to about the growth of your algorithm. So now the question is that in terms of time, if you have a computer and your computer can process like 1 million operation per second, so, and you wrote an algorithm that has different behavior, so the first algorithm can behave as actually log, and in terms of time, it will take like somehow, I don't know, 0.00199 seconds actually to process the 1 million operation. But if your algorithm is actually behave like 2 to the power of n, it will take 10 to the power of 300,000 years. So that's just only an example. Your computer, which is the good news, is faster than 10 to the power of 6. So most of CPUs is actually can process 10 to the power of 10 or 10 to the power of 11. This is the average. They are better than that. Also GPUs today is more faster, 10 to the power of 14, 15 per second. But sadly, still cannot save the exponential behavior when we are talking about to the power of n or factorial behavior. It's really hard. Here are some rules that you want to look at it. If we have a program and we want to calculate the complexity problem, okay? If the program behaves like 10 to the power, so this means like we have a nested loop and we repeat this nested loop, for example, 10 times. Constant number of repetition. The rule says that when you calculate the big O, now forget about calculating C times Tn. Okay, we just need a simple operation. You can drop the constant here. Say I don't need a constant. You can say that the time complexity of this 10 to the power of 2 is actually big O of n to the power. This is the complexity one. Now what if I have also plus a constant like 1000, for example, then you also drop it. You just look to the domain of the algorithm. If you have like 2 for loops, one for loop here, so this is a for loop that goes from 1 to n, and another for loop here, so this is a branch, this is finished. So this is not listed, so another for loop that go from 1 to n also as well, okay, or whatever j. So at the end you will replace these variables n and j by n, okay, and this is not listed. So this is actually the behavior of it is actually n, and this is actually big O n or j. But as I said, when we talk about j and n, it's any number. So then you can use the same number to represent them. So big O of n and this is big O of n. They are not listed, so you can sum them. Okay. Then you can say, okay, the complexity is actually big O of n plus n. And this is again will give us the same rule at the beginning. It's actually big O of 2 times n, and the constant is not needed, so you can drop the 2, so the complexity is actually big O of n. Okay. We have this multiplication. This is when it's nested. So if this for loop is inside this for loop, okay, you will do the multiplication n times n, and it's n to the power of 2. Then this is when it's actually nested algorithm. Sometimes it's actually like a collection of loops or blocks in your group program. The first block could be, for example, n to the power. The second block, which is not listed, maybe n. So then you say the complexity is n to the power 2 plus n. Then maybe you have another block, again is 2n, then plus 2n. But at the end you take the maximum of them, so the dominant. So you go to n to the power. And we have proven that in the previous example. I will explain this example and stop this lecture here, so I give you time to work with the exercises. Here is an example of a program that has 3 parts or 3 blocks. The first block is running a for loop from I to n, and it's do a constant work. okay? A printing statement, a formula, whatever, okay? Then we want first to calculate the complexity for the first part. Then we go to the second part, part 2, and then part 3, and try to sum the things up using the rules that we have explained in the previous slide. So for part 1, it is actually n, right? So you decide for part 1, you have a for loop. This is part 1, it's big O n. Then for part 2, if you think about it, it's actually a while loop, and inside that while loop, we have a for loop. Okay. Now let's look to the for loop in the inner side. Okay, so the for loop goes from j equal 1 to n. And this will never change. It's always from 1 to n. Okay? And we do a constant work there. So then the for loop, the inner, is actually big O of n. Okay, now this is part 1, this is part 2. We have big O n, but still we did not finish because we have the other while, and that's actually go until while m is greater than 1. But if you look down after the for loop, we always update m, and this is, we take the floor of m divided by 2, meaning that always we divide m. If m start by, say, 1 million, then we divide it by 2. So then this while loop will decrease very quickly, right? So this is actually, we are looking for halving the problem, okay? Then this, the behavior of the while loop is actually a logarithmic. It is a log m, or log n in this case. So it is times, because these are nested, then it's log n. Okay? So we solved part 1, we solved part 2. So this is equal this one, and this can be simplified to n log n. Okay, then part 3. Part 3 we have a while, and this start by n, and the while is actually, while r is less than n to the power of 2. We do some constant work, and then we increase r always like double the time. So then r will quickly reach n to the power of 2, because always we multiply it by 2. Then it's again, because it's not listed, nothing there, it's just only a while loop, then we have a logarithmic behavior, so it's log n. Then what we try to do is actually the calculation for them. Okay. This is part 3. And then we try to sum all things up, because this was a block, this is another block, this is a third block. Now we want to sum them. So we have big O n plus n log n plus log n. Then if you think about it, what is the dominant part for it? So which one is greater, n, log n? So log n is less than n. So this is a linear, this is a logarithmic, but we have n log n, which actually come as a greater than n. Okay? So then this is the dominant. So this is will be actually the overall behavior of my algorithm. Okay? The whole algorithm that we have. This is the worst case, I would say. Okay? And remember that when we say big O n log n, of course, n plus n log n plus log n is actually greater than this one. But if you put the big O beside it, then this means implicitly that there is a constant that if I multiply it by this, at some point n naught equal blah blah blah, you can calculate it. This will always be an upper bound for the overall behavior that I have. Good. I will stop my lecture here. Hope that we explained the things very well. Still, I have a couple of examples that I explain in my next lecture, and I will leave you with 2 weeks here to explain the exercises. Thank you, and have a good time.